All right, so our next speaker is Flower AI Summit regular, and he will be talking about a subject that we probably all have had to deal with at some point, that heterogeneity. Please welcome Dennis Grinwald.
Thanks a lot. Thank you for inviting me and being able to give this talk. Actually, I will be speaking about a project that I've been presenting last year at the Flower Summit in form of a poster. And back then, we submitted it to a conference. It didn't get through, but we got a lot of nice feedback during the conference, incorporated all of it, and finally we could make it to submit it to NeurIPS, and it was accepted last year. So yeah, thanks for being able to talk about this again. So what is federated learning? We all know it. We train a collaborative, a common model on a decentralized data set, and this process comes with a lot of challenges. One of which is the challenge of statistical heterogeneity, which I will be focusing mostly in this talk. So as we know, for statistical heterogeneity, the problem is that when we have very different data distributions on the clients, the optimal models diverge quite a lot from each other, which means that also the averaged model will be far away from the global optimum as well as the local minimum. One way to tackle this is personalized FL, where besides just having a shared global model, we also train and train local models on each client for the local data sets. And this also comes with a challenge that is, which is that usually these personalized models will be very dependent on the global model. So if the global model quality is really bad, then the personalized models will also fail. So ideally, we would want to not have just a single global model, but instead incorporate more degrees of freedom either within a model or maybe a group of models, and allow clients with greater similarity train more similar models that are more aligned to each other. Before diving into this, let's quickly recap the topic of mode connectivity, which is the observation that was made by Grinwald et al. In 2018, that if you have a set of randomly initialized neural networks and you all train them independently until convergence, there exist very simple paths in the parameter space that connect each of these models. And if you sample models along this path, each of these models will exhibit very low loss. And example paths could be a simple quadratic curve as the middle plot here, or piecewise linear functions. Interestingly, if you sample models along these paths, which you can see on the right, they all exhibit or they all result in different functions that are represented by these parameters, as shown by in the plot on the left. The works by Wartzman et al. Go a step further, and they try to enforce linear paths along different models, and they do so by, instead of just initializing a single parameter value, you instead initialize a whole simplex of values, and you train the simplex during training. So what you do during training is that for each mini batch that you sample, you also sample a point within the simplex and minimize the loss on it. This is very cheap because once you've sampled the model, you just compute the loss on it, compute backpropagation, and in the end apply the gradients to each of the endpoints, scaled by the coefficients that you used to sample the point from the simplex in the first place. So of course you have to store 3 times the number of values, as in this case it's 3, it could be more or less, but computationally it's almost the same as just computing a spare Fed average, but it gives us this exactly these degrees of freedom that we want, because basically instead of just training a single model, we have a full space of models that we can train here. We use these ideas in our method that's called FLOCO. So in FLOCO, instead of training a single deterministic model, we train a simplex of models across the clients. First, until a certain communication around tau is reached, we train the simplex in a uniform manner. So each client receives the simplex, samples uniformly from it for each batch, and optimizes the simplex. Once the simplex has been trained for tau rounds, we now proceed and project the clients into the simplex in such a way that similar clients end up in similar regions, meaning with similar clients, meaning they have similar data distributions. We do so by taking their gradients as a proxy value and employ a novelly developed projection algorithm that does exactly that. It groups our clients in different subregions of the simplex. So from now on, from communication around tau on, each client will only sample from the specific region that it was assigned to. And we know that clients that were assigned in the same region also exhibit the same data distributions or similar data distributions in the end. What this results in is a trained simplex that performs uniformly well on the global data distribution, so the concatenation of all the local client distributions. And we have specialized regions. For example, client 1 that belongs to one group with a particular data distribution now really specializes in a certain region of the simplex, and client 2 in a different region. This plot is just, or this table is just to show that we have compared and evaluated our method with several different state-of-the-art personalized FL baselines on many different data sets, many different non-IID splits with pre-trained as well as models that we trained from scratch. To wrap up, our method FLOCO beats state-of-the-art PFL baselines on local and global test accuracy and expected calibration error up to 10%. It's applicable to both randomly initialized as well as pre-trained models. It has a very small computationally overhead as compared to Fed average. Of course, the storage overhead is still there since we have to store multiple versions of the model. And promising future directions are the cross-device FL setting, because so far we have just applied it to cross-silo. And we want to see how this approach with training a simplex also applies to a different field of research, which is the field of model merging. Thank you so much.
Thank you, Dennis. We already have a question.
Very interesting crossover of optimization and federated learning. Does your methodology account for a distributional shift of your clients of how to potentially change over to a different area of the simplex or using a different model later on?
Yes, so in this work we didn't do that, but it's a follow-up thing that we are working on right now. Also, not only for clients that maybe change their distributions throughout their lifetime, but also new clients joining that lies somewhere in between clients that we haven't seen so far, but we think we could assign them the perfect spot in the simplex and adapt it accordingly. Yeah, great question.
All right, we also have a question here.
Thanks for the interesting talk. So I realized that you are grouping different clients, right?
Yeah.
So who does it? And also based on what information?
Yeah.
My point is, do they need to reveal some information to that party?
No, so that's a great question. The only information that we use from the clients are the pseudo-gradients. So basically the difference of the model that the clients sent us back after training and before training. This difference we consider as a direction, right? It gives us a gradient direction, basically, pseudo-gradient direction. And we use this information solely to project the clients and group them in similar regions.
Thanks.
Yeah.
Just to clarify, so you're revealing a little bit more information that you would do in standard federated learning?
No, actually not, because in standard federated learning, we sent a model, we received a trained model, right? And we use just that information. Taking the difference gives us a direction of optimization that this client has undertaken, so it's the same as Fed average. Yeah.
All right. I think
There's
sorry. Oh, good. I can pass the mic directly, I think.
Yeah, great. Thanks for the talk, and congrats on getting published in NeurIPS. That's cool. So the question was related to the previous question. So how do you deal with the sort of cycle? I mean, I think at some point if gradients are similar and you go to update them together, they become more similar. So it seems like there could be a collapsing effect.
Yeah, we haven't we haven't realized this collapsing effect because do I have training curves here somewhere? Maybe. Oops. Yeah, so here it seems like the effect is quite stable. So you can see a jump here. This is where we actually start a subregion assignment. Sorry for the small image here. Okay. Never mind. But in the end, we didn't notice any kind of collapse. I guess it could happen, But then what we also could do there, we didn't research this, but what we do is we sample for each client. We not only sample the single point that this client was projected on, but actually we parameterize an L1 ball around the client projected point that we use as a region to sample models from. And we could probably play with this radius more if we have such a collapsing effect. Yeah.
Cool. Thank you.
Yeah.
All right, that will be it for questions. Oh, all right, one last one.
Hey, thanks for the presentation. It was more out of curiosity, like when you present the idea, it reminds me of how the GPS localization works. I don't know if you got some inspiration from that, but I think it's a really nice comparison from the technologies.
Okay.
More of just a comment, not a question, actually.
Yeah, I haven't thought of this. This wasn't an inspiration, but interesting connection.
All right, thanks a lot.
Thank you.